In this video, I'll talk about some of the basics of carbon-13 NMR, and I'll do a few examples. I'll also talk about carbon depth 45, 90, and 135 in there as well. In addition, I'm going to be talking about the proton decoupled NMR, which means the carbon itself is not going to be coupling with the proton that it's attached to. And carbon does not couple with itself because of the relative abundance of carbon-13 is very, very small. If you focus on the two isotopes of the carbon, I mean, technically carbon has three isotopes at least, but if the most prominent isotope carbon is carbon-12, and then you have carbon-13, and then you have carbon-14. So carbon-13 only the isotope that is going to be NMR active. The carbon-12s, carbon-14 do not show up in the NMR, and the relative abundance of carbon-13 is so small that it doesn't really couple with another carbon atom that's right next to it. And these are all going to be decoupled from the proton, so you're just going to be seeing just the single signals. It's not as complicated as the proton NMR. So three things that you kind of focus on in carbon NMR is obviously the number of signals, which tells you the carbons that are not the number of carbons that are not chemically equivalent. And you do that in proton NMR as well. You try to figure out how many different types of protons you have in there, and that's the number of signals you get in the proton NMR. The second thing you look for is the chemical shift, and you do see that in the proton NMR. Now, unlike proton NMR, where the chemical shift kind of goes from 0 up to 15, the chemical shift in carbon NMR goes from 0 all the way to 220 almost. So we'll give you that example in a minute. And then the third thing, oops, and then you have the third thing, which is going to be the height of the signal. In proton NMR, you typically focus on the integrations and the multiplicity. You don't really use the multiplicity or the integrations in carbon NMR just because the relative abundance of carbon-13 is so low. The integrations and the multiplicity is not going to be there for the carbon-13, and it's not reliable. However, you can look at the height of the signal. However, it's not always going to be the most certain one or most reliable thing that you got out there, but sometimes you can, based on the height of the signal, you can figure out how many carbons are particularly belonging to that particular signal. So let's look at this molecule as an example, and I have in the carbon NMR, this molecule is on the right side. So I have this aromatic that got the OH attached to it, just like in a phenol, and then I got 3 carbons attached to it. And then I have the carbon NMR for this one. This is just a regular carbon-13 decoupled carbon NMR for this molecule. Now, if I want to figure out how many different types of carbons I got in there, just to run the plane of symmetry in there. So the plane of symmetry on this one is going to be right across the molecule vertically, so which means the left side of the structure is kind of the same as the right. The left side of the structure is the same as the right side of the structure. So I can say the number of carbons that are not going to be chemically equivalent, and that is going to give you a unique signals would be, I'm just going to randomly number those as 1. This is going to be 1 right here. This is going to be 2, and that would also be 2. This would be 3, and that would also be 3, because remember the left and the right side, they are chemically equivalent. They has an internal plane of symmetry in there, at least the vertical one. And then this would be number 4. And then you have these carbons, aliphatic carbon chain that's attached to this aromatic ring. This carbon, that carbon, they are going to be unique to one another. So I should be seeing another signal that's 5, 6, and 7. So altogether, I should be seeing a total of 7 signals for this particular molecule. Now, if I look at the NMR on the right side, I have 1, 2, 3, 4, 5, 6, and 7. So I do see 7 signals in there, and they are corresponding to those 7 chemically different um, carbon atoms that we just kind of designated on the left side of the molecule. So that's how you really want to look at it. Now, where they show up, so we got the number of signals down, where they're going to exactly show up. So you can use the carbon NMR table to figure out where they would show up. So typically, if you have a carbon that is just going to be either attached to a hydrogen or maybe another carbon or R group, the chemical shift for those, like for example, this one, that one, and even those guys right there, they're not attached to any electronegative element, so they're going to be fairly shielded. So they could show up anywhere between like 10 to 60. You can kind of see in here. But if you have a carbon that's attached to either, let's say, an iodine, a bromine, a nitrogen, chlorine, and even a fluorine. So that makes those carbons relatively deshielded. So as a result, they're going to be a little bit downfield. So when we say downfield, they're probably going to be somewhere a little bit down, maybe in the 50s and the 60s right there. So, I mean, the ranges can be off a little bit, but this kind of gives you a range of 0 to 40. This one is 25 to 65 when you have bromine attached. When you have nitrogen attached, nitrogen is more electronegative than the bromine and iodine, so that's going to be 40 to 60. Chlorine, that's 35 to 80. Oxygen, it's 40 to 80. That's fairly downfield because oxygen is even more electronegative than the nitrogen. So that makes this carbon even more deshielded. So if something is deshielded, it's going to go further downfield. So remember, deshielded, downfield, the D and D goes together. And then if you have, let's say, an alkyne carbon, that's going to be anywhere between 65 to 90. And then alkene carbon is going to overlap with the aromatic carbon. So both the alkene carbons are sp2 carbons, and even the aromatics are also sp2 carbons. So sometimes they can overlap with one another. A typical range for the alkene carbon is 100 to 150, and an aromatic carbon is 110 to 170. I would probably say 160 for the most part. They typically don't go all over to 170, but so I would say 160-ish where they're going to stop. But on average, if you don't have anything attached to the aromatics on average are going to be around 130 ppm. And then you have carbonyl signals, that's going to be the last thing. So carbonyl carbons, they're going to be fairly downfield because they are connected to the double bonded oxygen atom there. So you have multiple types of carbonyls. So you can have an acid and an ester and an amide carbonyl. They show up anywhere between 160 to 190-ish, I would say. And then if you have an aldehyde and a ketone carbonyl, they would show over 190 up to 220 in that particular case. So based on the chemical shifts that I see in this NMR here, I'm seeing stuff. This is 100, that's 110. So I'm seeing things over 110. They're kind of going all the way to 155 is 155, I would say. So that technically means they are going to be the double bonded carbon atoms or possibly the aromatics. And you do have an aromatic in here. So which signal belongs to which? I mean, or I can say at least I have 4 signals that are coming from aromatics. I got 1, 2, I got the third one here, and I got the fourth one. I do have 4 signals in the aromatic regions of this NMR here. And then I can also say that the signal 2 or the carbon 2 here and the carbon 2, there are 2 of them that are going to be chemically equivalent to, so they would show up at the same spot in the carbon NMR, and that relates to this number 3 as well. And I'm not sure why I wrote down 4 here, so this should have been 3 as well here. So that's going to be 3 and 3 here. So those carbons, since they are 2 as opposed to 1 and 4, they are by themselves. The signals that are going to be belonging to carbon 2s and carbon 3s must be double in the height. And you do see 2 signals right there. They are going to be twice the height of 1 and 4. So I would most likely say that this is going to be 1, this is going to be 4. And it would be hard to tell which one is 2, which one is 3. So one of them is a 2, one of them is a 3. It's not that easy to tell, but at least it gives you an idea. It tells you that, okay, these are aromatic, This is going to be twice. So you have two carbons belonging to this signal, two carbons belonging to this signal as well. And then you got three signals that are going to be in the aliphatic. So aliphatic carbons here, you have from 0 to like 40-ish. And remember, those are going to be the carbons that are just attached to other hydrogens or carbons, because that's what we have in that particular range. And the carbon I have here, which is just a CH2, that's 5. This is 6, and this is 7 right there. If I have to relatively talk about their shielding, 5, since it's going to be right next to the double bonded carbon, or I can say aromatic, 5 is going to be the most deshielded out of those 3 carbon atoms. So as a result, I'm going to say this is going to be 5, and this would be 6, and this would be 7. So 7 here should be the most shielded carbon atom, because it's away from a lot of like the aromatics or anything like that. So as a result, this should be most upfield. So it should be closer to 0 with respect to the TMC there. So we got this right there with the 7 here. Okay, so that's how you really look at it. Let's look at the depth actually. So you have a regular carbon-13 NMR that's proton decoupled, and then you have a depth 45, 90, and 135. So you can get some information about the depth NMR, whether you have the CH2s, CH, and a carbon by itself, or in a CH3. So a typical NMR, as an example, if whether it's in a carbon by itself and a CH, or CH2, or a CH3, a regular carbon-13 NMR is going to show up all of them. So I should see a signal for CH3 carbon, I should see a signal for CH2 carbon, I should see a signal for CH carbon, and I should see a signal for an C carbon. So you'll see all of them. But then when you start going to the other guys, like suppose if I go to depth 135. So whether it's 135, or I'm just going to write down depth 90 here, and this is going to be depth 45. So the carbon that's going to be by itself, it's only going to show up in the regular carbon-13 NMR. It's not going to show up in 135 or 90 or 45. So you're not going to see that anywhere. But then when you talk about the CH and the CH3, they would show up at 135 with a positive signal. So I should see a signal here and a signal here. That's going to be positive signal for a CH3 and the CH. And the CH2, however, in depth 135 would have a negative signal. So this is going to have a negative signal in that particular case. When it comes to the depth 90, the only signal that you see in depth 90 is actually the CH within a positive sign. So this is the only signal that you're going to be seeing in case of depth 90 in that particular. And then you're not going to see CH2 and you're not going to see CH3 either. So sometimes, when you run depth 135 and you see positive spins there or positive signals, then you don't know whether this belongs to like CH3 or the CH. That's when you run depth 90, because in the depth 90 you would see only in a positive signal for a CH. All other signals will not show up. And then on the other hand, when you have depth 135, the depth, depth 45 rather, typically depth 90 and 135 are good enough to kind of figure out what the structure is going to be. But the depth of 45 would also show up all the carbons except the quaternary carbon that's going to be by itself. So I should see a positive signal for the CH and a CH2 and in a CH3 as well. The only thing I wouldn't really see in case of an depth 45 would be the carbon by itself. But a lot of time, knowing about the 90 and 135 is good enough to figure out the structure of the molecule. Okay, so let's look at this example here. So I have CH H7Br. So the very first thing I want to actually do in here is figure out what the DOU going to be. So the DOU for this molecule would have been, I got 2 times 7 carbons plus 2 minus the number of hydrogens would be 7 minus the number of halogens would be 1 divided by 2. So I get, and that's 14 plus 2, that's 16. 16 minus 8, that's 4. 8, and that's divided by 2, that's 4. So I get in a DOU of 4. A typical DOU of 4 you get when you have an aromatic ring, especially a benzene ring. Because if you look at it in a benzene ring, it actually having a DOU of 4 because it's got 3 double bonds and it's got a ring, so that gives you a DOU of 4. But just because you get in a DOU of 4 or an IHG of 4, that does not necessarily mean you would always have an aromatic. But it kind of gives you an idea that you may have an aromatic. So to confirm that you have an aromatic, you may have to look at, let's say, an IR, or you may have to look at the proton NMR or carbon NMR. So suppose I'm given a carbon NMR in this particular case, and I know if it's an aromatic and if it contains carbon-carbon double bonds, for the aromatics, your carbon NMR shows up anywhere between 160 to 110 to 160ish, and aromatics on average are around 130. But they could fall in the range of 110 to 160ish. So that's the first thing I want to look for. Do I have those signals in there? So it kind of seems like I do have one signal here. I got one signal here, and I got a couple of signals here that you can kind of see how the height of these is a lot bigger than the height of the other two. So that tells you these probably be kind of representing more than one carbon. Now, if you just go based on the magnitude of the height, this is not doubled, but it's actually more than doubled. So that's why I told you earlier that the height difference is not always reliable. Like, you can use it, but it's not really always reliable that you want to use. Um, but I can certainly say that these signals right there, they're probably representing more than one carbon, which makes sense. I have 4 signals, but I have a total of 6 carbons in the aromatic ring, so that means 2 of them are unique and 4 of them are going to be, or 2 of them are the same and the other 2 sets are going to be the same. So maybe you have a dye-substituted ring. All right, so I got a dye-substituted ring where I can call this 1, and I call this 2, that would be 2, that would be 3, that would be 3, and this would be 4. So that means your 2s and 3s are going to be these signals right there because they are representing more than one carbon atom. So that is one thing. And then the 1 and 4, the 1 here and the 4 here, is represented by this signal right there and this signal right there. Now, sometimes it can be hard to tell, okay, which signal really representing 1 and which signal representing 4. That really depends on what do you really have attached to them. And sometimes you gotta do a little bit of math in that case. But, qualitatively, I can for sure say here that I have 4 signals that are belonging to the aromatic region, and as a result, I want to divide my aromatic ring, in such a way where I only get 4 signals. And you get only 4 signals if it's a dye-substituted ring, and more importantly, they are para-substituted, so that when you draw the line in the middle of the ring, one side of the ring is the same as the other side of the ring. So you're not counting those separate, but together. It's like you have 2s here and you got 3s here. Well, what else we got really left going on? So we have a bromine, and we got another carbon. So we have 1, 2, 3, 4. 4 hydrogens already taken care of. There's no hydrogen here. There's no hydrogen here. So that means I have 3 more hydrogens. So possibly I have a CH3 group, and then I have a BR, so possibly in a BR here. So it doesn't matter where you put the BR here or the CH3 here, it's the same thing. 4 signals, so you got 4 signals in the aromatic, but then you also have a signal that's going to be this one right there that's at 20. So that means that the signal around 20 should be fairly shielded, and it might be just in a carbon with attached to a bunch of hydrogens and maybe another carbon atom, and that is going to be this guy right there. So I can say this carbon, I can call this 5, and that would be number 5 here. And I can look at the depth 135 and the 90. So this is the depth 135. Remember, the 135 shows up the CH3s and the CH, and it would show the CH2s to be negative. But I don't really have any CH2 here, so you don't see any CH2 here because you don't see any negative signals there. And then the carbons that are by itself, they're not going to show up, or the carbons that does not have any hydrogens, they're not going to show up in the depth 135 and the depth 90. So this tells you that this is going to be a carbon by itself, this is going to be a carbon by itself, and then you have um, based on the depth 135, so these carbons could possibly be the CH or the CH3s. Well, we know that they are CH because they're in the aromatic, but let's suppose you didn't know that they were aromatic. So these could have been CH3s and the CH, and I could say the same thing. This could be a CH3 and a CH, and that's why you run in a depth 90, because in depth 90 only the CH shows up. So that means these guys are going to be the CH signals. All right, so that tells you this is in a CH, this is in a CH. And since you don't see any signal in depth 90 here, that means this must be in a CH3. So that's how you want to kind of read it in that particular case.